Good morning all. Today we will going to discuss numerical solution of ordinary differential equation, that is first part. Actually we are dividing our solution of ordinary differential equation into two parts, first part and second part. In first part I am discussing two methods, Euler's method and Runge-Kutta method of order 2 and order 4, and in the second part we will discuss finite difference method and predictor and corrector method. So in this slide we are discussing first Euler's method, then Runge-Kutta method of order 2 and order 4. Now, introduction. Many problems in science and engineering can be reduced to the problems of solving differential equations under certain given conditions. But all differential equations cannot be solved analytically, and hence the numerical solutions plays a very important role. Many techniques have been developed for approximate solutions of ordinary differential equations by numerical methods. The important methods described in your syllabus: Euler's method, Runge-Kutta method, predictor corrector method, and finite difference method. That Euler's method and Runge-Kutta method both are initial value problem, and predictor corrector method and finite difference method both are boundary value problem. Actually, what is initial value problem? Suppose our our differential equation given, and that initial point, our functional value should be defined. So that is initial value problem. For boundary value problem, if some differential equations are given and at that boundary point our functional value should be given, that is boundary value problem. Next, Euler's method. So consider the differential equation dy dx equals to fxy with initial conditions y of x0 equals to y0. Let y equals to phi x be the solution curve of the given differential equation dy dx equals to fxy. So we have to remember this: dy dx equals to fxy with initial condition y of x0 equals to y0. Let y equals to phi x be the solution curve of the given differential equation dy dx equals to fxy. Let x0 y0, x1 y1, x2 y2, xn yn, xn plus 1, yn plus 1 be the points on the solution curve. We suppose that the value of x are equispaced at equal spacing h, so that xn plus 1 equals to xn plus h. Already this is known to us. For numerical several times we discussed. Our points are equi-interval, so between two consecutive values of x, their difference should be same. Since the point xn plus 1 comma yn plus 1 lies on the curve y equals to phi x, so we have yn plus 1 equals to phi xn plus 1, that means phi xn plus h. Expanding phi xn plus h by Taylor's theorem, we get in the step length, we can expand it. So yn plus 1 should be written as yn plus h f of xn yn. Next term will be h square by factorial 2 f dash xn yn. Next term will be h cube by 3 factorial f double dash x to the power n y to the power xn yn, like this way. And since h is a step length and it will be very small, so we will neglect the higher power of h. Ultimately, we will get yn plus 1 equals to yn plus h f of xn yn. This is the Euler's formula. Using this formula, we will solve some problems. So we have problem 1. So that is the given condition dy dx equals to y minus x, y0 equals to 1. Using Euler's method, we have to obtain y for x equals to 0, 1 and correct to 3 decimal places. So first, this is the conditions given, that we will write clearly what is x0, y of x0 equals to y0. So x0 is 0. Our general formula of differential equation is dy dx equals to f of xy, y of x0 equals to y0. dy dx equals to f of xy, y of x0 equals to y0. So given dy dx equals to y minus x by y plus x, y of 0 equals to 1. Using Euler's method, we obtained y for x equals to 0.1 correct to 3 decimal places. So our x0 equals to 0, y0 equals to 1, h equals to 0.1. and f of x and yn equals to yn minus xn by yn plus xn. So we have yn plus 1 equals to yn plus h into f of x and y. Now putting n equals to 0 in 1, what we will get? Y1 equals to y0 plus h into f of x0 y0, that equals to y0 plus h y0 x0 by y0 x0. Then simply we will put the values of x0 y0, we will calculate the functional value and it will be 1.1. So actually we have to find the values of x 0, 0 0.02, 0 0.04, 0 0.06, 0 0.08, 0.1 and corresponding values of y. These are the values using this formula, and then we are getting that y1, y2, y3, y4, y5. Then the approximate value of y is 1.095. So this is the Euler's formula, and we will find the solution of this differential equation by Euler's method in this way. Again, you can see there is another given differential equation dy dx equals to x plus y of 0 equals to 1, h equals to 0.1. Using Euler's method, we obtained y for x 0, 0.1, 0.4, correct to 3 decimal places. So what we'll do? So here x0, y0, h, f of x and y all are given. x0 is 0, y0 is 1, h is 0.1, f of x and y. That means f of xy is x plus y. So f of x and y is xn plus y. And yn plus 1 equals to yn plus h into f of x and y. So corresponding values of n 0, 1, 2 up to n, xn 0, 0.1, 0.2 up to, we have to go up to 0.4. So from here we can calculate f of x and y. So we have x0, y0. What is y? First value of y0 is 1. Then we will calculate that functional value f of x0, y0, that is 1.0 here. Then we can easily calculate y1. y1 will be calculated from the Euler's formula, that is yn plus 1 equals to yn plus h into f of x and y. So we are calculating the value of y1 from the Euler's formula. Next we have the second value of n, that is 1. So corresponding xn is x1 y1. So x1 is x0 plus h, that is 0.1, clearly written here. y1 we will calculate y1 from here, that is 1.10. f of x and y, f of x and y is y0 is f of x0 y0, that is 1.02, that is 1.02. So y2 is 1.01. Like this we will get our y2 1.22. So then next again x2 y2, x2 is 0.02, 1.22. f of x2 y2, that is, we can calculate the functional value from this function f of x and y, that means x and y. So we are getting this way 1 plus 42. Next y3 we can calculate y3 1.22 plus 0.1 into 1.42, that means 1.362, like this way. Next is 0.3, we can calculate x and y in 0.3, y is 1.362. Then we can calculate f of x and y, that is 1.662. Again we have yn plus 1 equals to yn plus h into f of x and y. So we can calculate y3, according to we can calculate y4. Hence the approximate values of y at x is 0.1, 0.2, 0.3 and 0.4 are 1.10, 1.22, 1.362, 1.528. So we are taking our answers correct up to 3 places of decimal. So here is the answer. This is the Euler's method. Next, our next method is Runge-Kutta method. So Runge-Kutta method, there are two types: Runge-Kutta method of order 2 and Runge-Kutta method of order 4. So first we are discussing Runge-Kutta method of order 2. So we have this differential equation dy dx equals to fxy, and y of x0 equals to y0. Then the second order Runge-Kutta formula can be written as yn plus 1 equals to yn plus half k1 plus k2. Actually, we are getting the, after solving the differential equations, we are getting the values of y. We are getting the values of y. So, if n equals to 0, so we are getting y1. So, y1 should be y0 plus a small approximation. That means small correction. Here correction is half of k1 plus k2. So from this formula we can find k1. K1 is h f of x and y. K2 equals to h f of xn plus h yn plus k1. Fourth order Runge-Kutta method. So fourth order formula is k1, k2, k3, k4. H f of x0 y0. H f of x0 plus h by 2 y0 plus k1 by 2. K3 h f of x0 plus h by 2 y0 plus k2 by 2. K4 h f of x0 plus h y0 plus k3. Then y1 equals to y0 plus 1 by 6 k1 plus 2k2 plus 2k3 plus k4. Therefore, in general, yn plus 1 equals to yn plus 1 by 6 k1 plus 2k2 plus 2k3 plus k4. Therefore, our k1 is h f of xn comma y, k2 h f of xn comma xn plus h by 2 comma yn plus k1 by 2, k3 h f of xn plus h by 2 plus comma yn plus k2 by 2, k4 h f of xn plus h yn plus k3. This is the Runge-Kutta method of order 4, because here we can see that we can find this in implementation or this increment by using these four variables k1, k2, k3, k4, and previous case we are getting these values using two variables k1 and k2. This is Runge-Kutta method of order 2. Actually, we are solving the differential equations, and this is initial value problem. Our functional values are given at the initial steps. So there are two steps k1, k2. With the help of this, we are getting the with the help of k1 and k2. So we will give the increment on our solution in each step. So this is our Runge-Kutta method of order 2, and here we can see that there are four values k1, k2, k3, k4, and we combine it. So this is actually our differential equation. We have this differential equation dy dx equals to f of xy, f of xy, y of x0 equals to y0, dy dx equals to f of xy, y of x0 equals to y0. So we have to solve it. We are solving, we are getting the values of y. So when, if this is our formula, if n equals to 0, we are getting the values of n equals to 0, we are getting the values of yn equals to y1 equals to y0 plus k, y0 known to you. Actually, k is written in the term of 1 by 6 k1 plus 2k2 plus 2k3 plus k4. 1 by 6 k1 plus 2k2 plus 2k3 plus k4. And that k1 is calculated from this formula h f of xn y, k2 h f of xn plus h by 2 yn plus k1 by 2, k3 h f of xn plus h by 2 comma yn plus k2 by 2, k4 h f of xn plus h yn plus k3, like this way. This is the Runge-Kutta method. So we can discuss both Runge-Kutta method of second order and fourth order. For second order, two variables are involved k1, k2, and for fourth order, four steps are involved k1, k2, k3, k4. Now here is the problem. So given dy dx equals to x minus y, y of 1 equals to 1, using second order Runge-Kutta method, and obtained y for x equals to 1.1, correct to 3 decimal places. Now here h equals to 0.1, that is not given. So here we are assuming it. If h is not given, we will assume it is as least value, and we are considering h as 0.1. So now for n equals to 0, our k1 is h f of x0 y0. So we can easily calculate. What is the formula? Our formula is for Runge-Kutta method of second order yn plus 1 equals to yn plus k. What is your k? K should be half k1 plus k2. That means we have to calculate k1 and k2. So k1 is, what is k1? K1 is age f of x0 y0. So x0 y0 known to us from here, and we know our differential equation, standard form of differential equation, dy dx equals to f of xy, dy dx equals to f of xy, y of x0 equals to y0. dy dx equals to f of xy, y of x0 equals to y0. So x0 y0, x0 is 1, y0 is 1. If we compare, what is our fxy? If we compare the standard differential equation, our fxy is x minus y. Fxy is x minus y. X0 is 1. Y0 is again 1. But h is not given here. So we will calculate our h. Actually, we have to find the value of x at 1.1. So x0 is 1. So we can easily say that h is 0.1. Just we assume it. Then we can easily calculate k1. K1 is calculated from here and it is 0. Fxy is given. Similarly, we can calculate with this formula, calculate k2, h f of x0 plus h, comma y0 plus h, y0 plus k1, y0 plus k1. K1 is already calculated. We can easily find y0 plus k1. Then we can find the functional value. Then we can easily calculate k2. So when k1, k2 is calculated, we can easily find out k1. This is the case, and y of 1.1 is the 1.005. This is we are using by Runge-Kutta method of order 2. Similarly, we can solve any problems by Runge-Kutta method of order 4. Next, our next example, example 2, apply Runge-Kutta method of order 4. Find an approximation value of y for x equals to 0.2 in steps of 0.1 if dy dx equals to x plus y square, given that y equals to 1 when x equals to 0. So here fxy equals to x plus y square. So same procedure, our formula is, our differential equation is of the form dy dx equals to f of xy, dy dx equals to f of xy, y of x0 equals to y0. That is the first case. Okay, if we compare, our fxy is x plus y square, x0 is 0 initially, initial value of x is given, that is 0, y0 is 1, and we will take h as 0.1. Now for Runge-Kutta method of order 4, what is the Runge-Kutta method of order 4? Actually, we will solve the differential equation. We are getting y1. Y1 should be y0 plus k, where k is 1 by 6, k1 plus 2k2 plus 2k3 plus k4. This is the k. So actually, this is our answer. Y1 equals to y0 plus k. We will calculate k from these variables, k1 plus 2k2 plus 2k3 plus k4, where k1 equals to h f of x0 y0, k2 equals to h f of x0 plus h by 2, comma y0 plus k1 by 2, k3. K3 is what? H f of x0 plus h by 2, y0 plus k2 by 2, k4. H f of x0 plus h, y0 plus k3. So we can calculate easily k1 if we have to find out the value of y1. So we will calculate in these steps, we will get the answer. But if we have to find out the value of y2, y2 will be y1 plus k. So K new will be calculated in this way: K1 new plus 2 K2 new plus 2 K3 new plus K4 new by 6. Again, you will get K1 new equals to h f of x0 y0 is for previous one. Now for this is x1 y1. Then we can calculate K2 for h into f of x0 plus h by 2 y0 plus K1 by 2. For K3 h f of x0 plus h by 2 x1 plus h by 2 y1 plus k2 by 2. For k4 h f of x1 plus h y1 plus k3. So we can calculate. Again, if you need k y3, then it will be changed accordingly. K4 we can easily find all these values. So here first we are putting n equals to 0. We are calculating k1 in this way. K2 already I discussed, this is the value of K2, this is the value of K3, and this is the value of K4. So here we are getting Y1. Y1 is actually Y of 0.1. Y of 0.1, but we have to find the value of Y for X of 0.2. That means actually we have to find out the value of Y2. We will calculate Y2 same way. So we will choose n equals to 1. Then we will calculate k1 is h f of x1 y1. Already known, everything is known to us, and by simple calculation we are getting these values. Similarly, we can calculate k2. K2 is this way, and after calculation we get this value. So next k3. This is the formula for k3, and we will calculate it, and we are getting these values. K4, and we are getting k4 in this way. So hence y2 equals to y of 0.2. That means y1 plus 1 by 6, k1 plus 2k2, 2k3 plus k4. Then we'll get this value. So this is the actual solution. And here there is one problem. Errors in solution of ordinary differential equation. So error in Euler's method. The truncation error in Euler's method is, we have to remember it, and its order is h square, and this belongs to x0 less than epsilon less than epsilon. That means first value and the last value of x. And Runge-Kutta method has truncation error of order hq for second order, and for fourth order truncation error is h to the power 5. And here is a problem that, oh, so thank you. Actually, I have one problem for students, but now this is not in PPT, so I'll give you later. Again, I'll recall all these discussion, this lecture. Actually, in this lecture we are discussing Euler's method. So there are two methods in your syllabus. There are two methods for initial value problem, and there are two methods for boundary value problems. Euler's method, Runge-Kutta method, Page-Descartes method, and finite difference method. And there is Euler's method. So this is the Euler's method. And there is one example we discussed with the help of Euler's method, and another one example solving the differential equation by Euler's method. And here the Runge-Kutta method of second order. This is a formula yn plus 1 equals to yn plus half k1 plus k2, and this is the formulas how to calculate k1 and k2. This is the Runge-Kutta method of order 4. So this is k1, k2, k3, k4, and how will you calculate? This is the formula. Then we are solving one problem on Runge-Kutta method of order 2, and next we are solving one method with the Runge-Kutta method of order 4. Then this is the case, and this is the error calculation of Euler's method and Runge-Kutta method. And thank you.